Okay, welcome back. Now in this lesson, we're going to talk about electric field. Now there are a few things we want to talk about. In the first part, we want to talk about what is electric field. So we will talk about what is represented. What is field? What is a field? We have heard about gravitational field. Now we're going to learn about electric field, and we are going to learn about magnetic field as we go on, okay? And we are also going to learn how to represent it in drawings. How do we draw? How do we represent electric field? Okay, do we use lines? How should we point the arrow? And finally, we're going to look at some examples. Okay, so let's get started. Now, what is electric field? Now, we are very familiar with the word field. So field, just like soccer field, rice field, it is talking about an area. It is talking about a region. So likewise, when we talk about electric field, okay, so when we specifically talk about electric field, we are talking about an area or region around a charge where something is experienced. What do you think it is? An electric field is an area or region around a charge where a force is experienced by who? By another charge in the field. So this means that whenever we talk about electric field, magnetic field, gravitational field, it is always trying to tell you that in this area or in this region that's surrounding this charge, there will be a force that will be experienced by a fellow charge. Okay, so let's give you an example. Okay, we know that if I have a positive charge over here, there will be an invisible area or region around it. We call it electric field. So there will be a certain field. It is not visible to the eye, but how do we know that there is a certain amount of electric field around it? All we need to do is to bring another charge near it and we observe. Okay, so for example, if I were to bring a negative charge near it, we know that the negative will be attracted. There will be a force of attraction that is exerted on the negative charge. So therefore, because of how the negative charge moves, we know the presence of the electric field surrounding the positive charge. Okay, so whenever we talk about field, is always related to a force that's being experienced as well. Okay, another example, we take a look at gravitational field. It is the same case. If Earth have a gravitational field surrounding it, how do we know the presence of this gravitational field? All we need to do is to ask yourself, if I place a 1 kg object in the midst of the field, of the electric field, it will experience a force of attraction, right, of 10 Newton to the Earth. So whenever the object is in the presence of the field, a force will be experienced. So even though fields are invisible to the eye, you just need to look at how the objects get pushed or pulled in the field. You know that there is a field surrounding it. Now, how do we illustrate? How do we draw this invisible field? Okay, so in the scientific world, in the community, this is how we represent field. So how do we illustrate? How do we represent the presence of field? Now, there are two things you need to include. The first thing is you use lines to represent, which we will see in a while. Number two, you will use an arrow to represent the direction, okay? Now, what direction you would ask, okay? So this arrow direction represents the direction of force on a positive test charge in this case. So give you an example, okay? If I were to, how do we represent a few lines of a positive charge? So let's say I have a positive charge here, okay? I cannot possibly draw this dotted line to represent field. Now, this is not acceptable. We cannot draw a few lines using dotted lines surrounding it. What we must do is use the appropriate lines and arrow. Now, first and foremost, ask yourself, what happens when you bring a test charge or a small positive charge near it? So if I were to bring a small positive charge near this main positive charge, we know that like charges repel. And so it will be pushed away in this direction, outwards radially. So this shows you the direction of the field lines. So when you draw your field lines represent the direction of the push on this positive test charge. So when you draw your field lines, it is pointed outwards because it follows the direction of the force exerted on this positive test charge. And it will be in all directions. That means no matter how the positive test charge comes near it, it is always a repulsion. So these are known as electric field lines. So your electric field lines tells you how a positive test charge would move if placed near it. Let's take another look at another example. How about a negative charge? How do we represent the invisible electric field around the negative charge? Again, you take a positive charge near it. And we know that since unlike charge attract, there will be an attraction towards the center of the charge. So therefore, your electric field lines will follow the same direction. It will be an attraction to the center no matter how you introduce the positive charge. Okay, so this is how you represent the electric field lines of a negative charge. So bear in mind, to represent field lines, you need lines. Okay, so this, if it's a single charge, these are straight lines. Okay, for a single charge, it will be straight. Later on, we will talk about what happens if there's a plus and a minus. And not just that, you must show arrow. Now, the arrow doesn't just point any direction. It depends on the direction taken by the positive test charge. So when you bring a positive test charge near an unknown charge body, so in this case, if I bring the positive test charge near to a plus, I know that it will definitely be repelled outwards, and therefore electric field lines are pointing outwards. Whereas in a negative, when you draw the field lines of a negative charge, when you bring a positive test charge near it, I know that you'll be attracted towards it, and therefore the field lines represent a pull towards the center of the charge. Now, how do we represent the field lines if there are more than one charge? Okay, so give you an example. Let's say if we have two charges of like charge plus and plus, when I bring them close together, okay, so recall that the field lines, the electric field lines surrounding the positive test charge is pointing outwards. But if I have two of them that's nearby, so if these are two positive charges that are near to each other, okay, it must be near so that it can be in the field. They must be in the electric field in order to experience the force. So therefore, we know that like charges repel. All right, so therefore, when you draw, the field lines represent the direction of the repulsion. However, bear in mind that the field lines at the center will be slightly curved because it shows that the field lines, that the forces on a test charge will be pointing away from each other. Okay, so this is how you indicate the field lines surrounding two like charges. So again, how do I come up with the field line direction? Think of the positive test charge. So when I bring a positive test charge near it, it gets repelled, right? So your field line should represent the same direction. So when I place the test charge near any part or anywhere near the field, it will be repelled away. And so my field lines represent that. Now, so what happens is right at this interesting spot here is what we call the neutral area. Okay, so when it's neutral, it means that it does not experience any force. Why? Because forces cancel out each other. All right, so this is a neutral zone. So therefore, when I place a test charge here, it will remain there because there are no forces that will be applied on it due to the cancelling of the effect. Let's take a look at what happens if it is two negative charges, two like charges. So again, how do I draw the field lines? I imagine that I put a test charge here. I know that the test charge, the positive test charge will be attracted to it in this direction. So when I draw my field lines, it will be in the same direction as the positive test charge. And once again, right in the middle is where the neutral zone is. So your field lines will represent that. Okay, they curve away due to the light charges. Okay, so now take note of an important thing, and that is your field lines cannot touch each other. So meaning to say you cannot draw something like this. Okay, you have one field line and then another field line. Okay, they should not touch. This is a bad example. Okay, now let's take a look at what happens if it is a plus and a minus charge. How would the field lines look like? So if it is a positive and a negative, again, the field lines point out of plus and into the minus. So your field lines will point this direction. How do I know? Again, take a positive test charge. When you put it here, when you place a positive test charge right here, you know that it will be repelled from the positive and it will be moving to the right towards the negative. So you realize the electric field lines represent that. Okay. However, because the field lines will get weaker as the positive test charge moves away, so it is curved in such a manner as the positive test charge gets further. Okay, so therefore this is how you can represent. You can draw. So remember, your field lines should not touch each other. Okay, so therefore, if you were to take a positive test charge, if you place it here, it will move away in the same direction as the field lines. If you put a positive test charge here, you realize that it will move in the same direction as the electric field lines. So your electric field lines tell you exactly how the positive test charge would move. Now, one thing to also take note of is the strength of the field lines is represented by how close the field lines are. So the strength of the field, okay, can be shown by how close the lines are. Okay, so give you an example. Let's say we have three parts of the view. Let's say we take this part here. Let's say this point P versus point Q, for example. You realize at point P, the field lines are closer together as compared to at position Q. So therefore, the field at P is stronger than the field at Q. Why? Because the field lines are closer together, and also naturally because it is closer to the charge. Now, another example that they will show you is on parallel plates. So what happens is when you have parallel plates, so these are metal plates usually, and when you connect them to the plus and the minus part of a battery or a cell, okay, it will cause the plate that is connected to the plus side to be positive, whereas the side of the plate that's connected to the negative terminal of the cell to become negative. Okay, so how do you illustrate the field? Again, you take a positive test charge and you put it here. And you know that when you place a positive test charge here, it will be repelled from the positive plate and it will go straight to the negative plate because unlike charges attract. So when you draw your field lines, it will be in the same direction. So for parallel metal plates, this is how the field lines look like. Okay, so typically in the middle, the field lines are parallel. However, as you move further and further away from the plates, the field becomes weaker. So at the end, it's actually a slight curve. Okay, so that is how you draw the electric field lines between parallel metal plates. So I hope you find this useful.